Welcome back. In this episode, we enter one of the most serious weather threats in aviation, aircraft icing. Icing can reduce lift, increase drag, and disrupt instruments all in just seconds. Today, we'll cover how it forms, the types of icing, and where it's most likely to occur. Let's begin with the basics. Icing forms when supercooled water droplets freeze upon contact with the aircraft. These droplets exist in clouds or precipitation between 0 degrees Celsius and minus 40 degrees Celsius. The risk is highest around minus 10 degrees Celsius. Supercooled means the water is below freezing, but still liquid. When it hits a surface like your wing, it freezes instantly. This adds weight, alters airflow, and can severely impact aircraft performance. There are three main types of airframe icing: clear ice, rime ice, mixed ice. Each forms under different conditions, and all are dangerous in their own way. Clear ice forms when large droplets spread out and freeze slowly. It's smooth, transparent, and heavy. It often builds on the leading edges and trailing parts of wings, and can stretch beyond the protected areas. Clear ice is most common in cumulus clouds or freezing rain. It's hard to detect and remove, especially in flight. Because it forms in layers, it can grow thick quickly, making control more difficult. Rime ice forms when small supercooled droplets freeze quickly on impact. It's rough, opaque, and lighter than clear ice, but it disrupts airflow more because of its uneven surface. Rime ice typically forms in stratus clouds, where droplets are small and spread out. Though it's easier to detect, it still causes serious lift loss and stall risk if not removed quickly. Mixed ice combines features of both. It forms in clouds with a mix of droplet sizes, common in frontal zones or layered weather. It's irregular, builds fast, and presents the most challenging in-flight scenario. Let's now talk about where icing is most likely to occur. Cloud layers between 0 degrees Celsius and minus 15 degrees Celsius. Frontal systems, especially warm fronts and occluded fronts. Mountainous terrain, due to orographic lifting. Freezing precipitation, such as rain or drizzle. Icing can occur at any altitude, but is most common between 5,000 and 20,000 feet, especially where moist air meets sub-freezing temperatures. Let's run through a real-world example. You flying through a stratus layer at minus 5 degrees Celsius. After 2 minutes, you notice degraded climb performance. Looking outside, you spot dull, white ice on the wing's leading edge. That's rime icing in action. Or imagine descending into a layer of freezing rain. The outside air temp is minus 2 degrees Celsius. Large drops are sticking and spreading on your windshield and wipers. That's clear ice, and it can build alarmingly fast. One major hazard of icing is the loss of lift. Ice changes the shape of the airfoil, leading to higher stall speeds and more drag. Even small amounts can reduce lift by 30% or more. Ice also increases the weight of the aircraft, especially on smaller general aviation planes. This impacts your climb rate, fuel efficiency, and ability to hold altitude or make a missed approach. Control surfaces become less effective too. Elevator, aileron, and rudder responses may feel delayed or sluggish. In some cases, ice-induced tailplane stalls can occur during descent or flap extension. Let's talk about tailplane icing. Unlike a regular wing stall, a tailplane stall pitches the nose downward suddenly and forcefully. It often happens when deploying flaps or increasing speed through precipitation. Warning signs include unusual control pressure, sudden pitch changes, elevator vibration. If this happens, retract flaps, reduce power, and gently recover pitch. Don't pull hard, this worsens the stall. Now let's mention pitot-static system icing. Ice can block your pitot tube or static port, causing inaccurate airspeed, altitude, and vertical speed readings. That's why anti-ice systems for these instruments are critical. Pitot heat is standard on most aircraft. But if it fails or you forget to activate it, you may see sudden airspeed drops, static readings, or erratic climb descent indications. Always monitor for inconsistencies. Let's also mention propeller icing. Ice can form on blades, reducing thrust and causing imbalance. Most prop aircraft have electrical or fluid-based de-ice systems, but they require monitoring and timely activation. Now, let's shift to engine icing. Ice can form in two places. Carburetor icing, caused by vaporization cooling in the carb throat. Intake icing, ice accumulation at the engine inlet. Carburetor icing is common even in mild weather around +10 degrees Celsius with high humidity. Always apply carb heat if you notice engine roughness, RPM drop, or poor throttle response. Jet engines can also suffer from fan blade icing or inlet blockage. Modern engines include anti-ice systems, but failure to use them can lead to compressor stalls or flameouts. Let's quickly talk about icing on the ground. Frost, freezing rain, or snow can form before departure. Even a thin layer of frost can increase takeoff distance and reduce lift dramatically. Pre-flight inspections must include all critical surfaces, wings, tail, control linkages, probes, and sensors. If anything is iced, don't fly until it's de-iced and clean. Contaminated takeoffs are a leading cause of winter accidents. Even in VFR, don't assume you're safe from icing. Flying through visible moisture in freezing temperatures is a real risk. That includes mist, fog, clouds, drizzle, or rain. Let's wrap up part 1 with key takeaways. Icing forms from supercooled droplets between 0 degrees Celsius and -40 degrees Celsius. Clear, rime, and mixed ice all affect lift, drag, and control. Engine and instrument icing can occur fast if unprotected. Always know the forecast, monitor outside temps, and respond early. In part 2, we'll go deeper into icing forecasts, onboard protection systems, and how to avoid and escape icing in real time. Don't miss it, it could save your flight. See you in Meteorology number 36, Aircraft Icing, Part 2.